Hi, my name's Andy, and in this series we're going to talk through how to write a programming language. We're not going to go into the really hard bits of it. We're going to try and get the general ideas across. The way we're going to do that is talk about a language I wrote specifically to try to be comprehensible and simple, which is called Cell. We're going to talk about how that's implemented. This video is about the Lexer, which is the first bit of a programming language I think we should talk about. I'll show you what we're going to talk about. We'll start off with just what do we mean when we say programming language. Then we'll talk about what a Lexer is, which is something that spits out these things called tokens based on your source code. Then I'll briefly talk about what Cell is, and then we'll do the main body, which is figuring out or explaining how the Lexer in Cell actually works. So first of all, what is a programming language? It is something that takes in a text file, does something, and then it either produces behavior or it produces an executable file, which is a file that can later on produce behavior. For the purposes of this video and the next few in this series, maybe we'll do compilers later. Excel has a kind of a compiler, but I think it's rubbish, so maybe we won't do compilers, but we will do interpreters. This is how interpreters work. They take in text, they do something, and then some behavior comes out the other end. So let's break that down a little bit more. Get myself out of the way. So what a programming language, how most programming languages are structured, is that they take in some source codes in the form of text, and then the Lexer breaks up that text into tokens. That's the job of the Lexer, and this is quite a dumb job, and that's what we'll be looking at in this video. And then the next step is that the parser takes in the tokens and produces a syntax tree, which is a kind of structure for those tokens that fits their meaning. And once we've got a syntax tree, at least in our interpreter, what we're then going to do is pass it on to the evaluator, which is basically the thing which produces behavior based on the source code that you typed. So this is the bit we're talking about today, taking in some source code and producing these things called tokens. Which are basically very dumb bits of just the sort of underlying structure of the code you typed. So things like a number is a token. So here's an example of splitting up some source code into tokens. So at the top we can see some source code, foo equals bar, and where bar is a string. In Cell, everything tends to end with a semicolon. It makes the parsing easier. So at the top, we've got the source code from a Cell program, and then at the bottom, we've got the tokens that come out of it. So in Cell, Cell's written in Python, and the tokens that the Cell's Lexer produces are these little tuples with the name of the type of token on the left, and then the contents of the token on the right. So foo is a symbol, so its type is symbol, and we also need to know which symbol you actually typed. So the right hand side is foo in that top line, and then the second token is the equals sign, but equals signs are special, so they have their own type that's just for them. So the type of an equals sign is just equals and doesn't have any contents. Then the third token in that piece of source code is that string, quoted string. So the type of that is string, and the contents of it is bar. Finally, the last token in that bit of source code is a semicolon, which again is one of these things that has its own type. So semicolon is the type, but it has no contents. Notice that the quotes have been removed from bar, so the contents of the token bar is just bar. We know it's a string because its type is string. Here's another example. There's some source code at the top, which is just 200 minus 158. And we break that up into tokens. and the type of the first token is number, and its content is 200. And then we have a minus sign, and then the type of the second token is number, its content is 158. Okay, so here's a little bit about Cell. Cell is a programming language that I wrote, which is designed to be basically as short as possible in terms of how much code there is in the code of the programming language. So when you write code in it, you may not write short code, but when I wrote the programming language, there isn't much code. And the idea of that is so that you can understand how it works. It's really quite painful to use. I've been trying to use it to write a Cell interpreter in Cell. It's pretty painful. You can find it on GitHub under j.p.beaubien/cell. I'm just going to quickly show you it working to prove that I've really done it. So if I just start Cell's interactive interpreter or REPL, I get a little prompt like this. I can define a variable called something like x, set it to 3, and then I can define a function called double by doing this. So this input is the name of the argument to the function, and then to return something you just say it. You don't need to say return. So the return value of this function is 2 times input, and then curly bracket to finish writing the function. And now I can call this function double and pass in x, and I'll get back 2 times the input I passed in, so the answer is 6. So it maybe looks a little bit like Python code in a kind of naive way. Actually underneath it works like this, but you don't have to worry about that. And for this video, we're not going to care really about how any of that stuff works. We're just looking at how to break it up into different tokens. So here are some more examples of what we can do. Basically the same kind of stuff, creating a variable called num1, and then creating a function called square, which does x times x, where x is its input, its argument. And then you can call a function in a sort of Python-like style. So Cell's Lexer only knows about these types of things. Numbers, which could be something like 12, or it could be something like 4.2, so decimals are included in that token type called number. They could be strings, which could be surrounded either by double quotes or by single quotes. They could be symbols, which are just words with no quotes around them. They could be operators like plus and minus. And they could be some special punctuation, like brackets, commas, curly brackets, curly braces. That's all we have to do in the Lexer. All we have to do is we're given some characters coming out of a text file, and we have to break them up into tokens and say what type each token is. And here is the lexing function of Cell. So if you go to that GitHub page, you'll find code almost exactly like this. The actual lexer.py file is something like 40 lines long. It really is very short. You should be able to understand it, or at least that's the idea of it. But here is the really core key function. It's called lex. It takes in a stream of characters. You can think of this as being just like a normal iterator of characters. It's called chars. Actually, it's I made a little class called peekable stream, because I need to see which one is next before I actually move on to the next one for some of my stuff. So it's pretty much like an iterator. We just we get given this thing called chars, which is some characters that are coming from the source code, and we're just going through them one by one. And this big if block here, if, elif, 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 if, is the real core of our Lexer. And basically, we get here every time we're about to start a new token, and then we just get the first character of that token, and that, in this case, in this Lexer, that one token helps us know that one character helps us know what type of token this is. In other more complicated Lexers, you might need to look at several characters at the beginning of the token before you're certain what type of token it is. One of the things that's nice and simple about Cell is that the first character always tells us. So let's look at the first bit of that if first. So if the first character is either a space or a new line, we do nothing. So essentially, we're not actually starting the next token. We're doing nothing. So we just skip, and we'll go on to the next character. So that was easy. Then the next step is that if we're looking at a plus or minus, a times or a divide sign, then we've immediately finished lexing this token. So what we're going to do is yield this token with a type of operation, which is what you get for a plus or minus, times or divide, and the contents of the token is the actual character that we found. So this is a token that's 1 character long. Just a quick little bit of explanation about what yield does if you haven't seen that before. So this code is Python, and this function returns an iterator. So you can think of yield as basically being saying to the outside world, here is your next value in your iterator. So yield basically says, I found a token, its type is this thing says, I found a token, its type is operation, and its contents is just this 1 character C. And we're just kind of throwing that out to say this is the next thing in your iteration. If you're iterating through the result of this function, your next thing will be this tuple operation comma C. I hope that made it clearer. Maybe it didn't. So that deals with all the arithmetic operations. If we find a plus, minus, times or divide sign, we immediately say, this is a token we know about. So if we found another plus immediately after the first plus, well, then there'll just be 2 tokens, plus and then plus, which doesn't make sense in the language, but is fine from the point of view of the Lexer. No problem about that. It'll just provide 2 tokens, a plus and then another plus. So let's move on to the special characters. So these brackets, curly braces, comma, semicolon, and so on, they're all special. That means they have special meaning to the parser. So when we start building a structure onto this code, each of these is going to have a particular meaning. So we don't need to do anything clever at all here. All we say is each of these characters is only ever 1 character long. Cell doesn't have any special characters that are actually longer than that. For example, 3 curly braces in a row, or equals equals sign, or anything like that. So we can immediately yield this token, and its type is going to be the actual thing we found, because these are all so special that they get considered as their own type. And then when the parser's getting a stream of tokens in, it can immediately just say, well, if I've got a curly brace, do this, and if I've got a comma, do that, and it treats each of them specially. So that's why they get their own type. Then the next line in our lex function deals with strings. So basically, the beginning of the token was either a single quote or a double quote, and we are going to yield up a token called string. But the contents of that token, we're going to yield up a token with type string. But the contents of that string are going to be the next characters after C. So we haven't actually got them yet. So what this code does is it says yield and then gives the type of string, but then the right hand side, the second value in the tuple, is going to be the result of calling a function called scanString, passing in that first character we found and the chars that we're looping through. And actually inside scanString we're going to move on through more characters. So although this loop looks like it touches every character, actually when we call scanString we scan forward through chars. So this loop won't go through every character, it'll have skipped. By the time it gets to the next move next call up the top there, it will have skipped past some of the characters. That's a slight complication, and it's not my favourite style, sort of mutating values that we pass into functions. But well, when you haven't got many lines of code, this seemed the best way to handle it in Python. Anyway, the point is, as soon as we find a single or a double quote, we know we've got a string, but what we've got to do is go and find all the rest of the characters in that string. And then they are the value of this token. We already know that the type is string. So let's have a look at the scanString function. Here's the scanString function. It takes in delim, which is a single quote or double quote. So it knows when the string ends is when it hits another character, the same as delim. It takes in those characters that it's looping through. So it just does a while loop saying, well, we haven't got to the close quote, which is this delin value. Move to the next character. If we've hit the end of our input, because C is none, because that means the end of our input, then we're going to throw, because we haven't finished our string. We've got to the very end of the file, and you haven't finished off the string. Otherwise, our return value just gets that character added onto it, so that that ret is going to get returned at the end. So we just loop through, keep going until we hit the close quote, adding all these characters to this return value ret. The only thing we have to remember is that stuff in green at the end. Once we've hit that close quote, we need to just move on one more character before we give back control to the main lex function. Otherwise, we're going to think we're starting another string, and actually we're just ending the first one. So back into the lex function. Now we've done the string stuff. Now we're on to the next elif, which is looking for the first character, identifying that this thing we found is a number. And we're doing it with a very simple regular expression here, which is just a regular expression which is applied to the first character, which just says, if you find either a full stop or a 0 to 9, then this is a number. So that the square brackets there just mean any of these characters inside here, and then dot 0 minus 9 just means a dot or 0 to 9. So anything that starts with a digit or a dot is a number, so we immediately yield saying the type is number, but then again we need a scan function to go and find all the rest of that number before we can find the actual value of the token. So we'll have a look at that scan function. Notice that we pass in the first character that we found and the rest of the characters so that we can loop through finding the other bits of that number. And we also pass in a regular expression saying these are the other characters that I would expect to be in a number. So when you stop finding those, you've finished with your number token and you can yield it up. So here's the scan function. It takes in the first character, the characters we're looping through, and then a regular expression to say what's allowed to be part of this token. And we're going to return, so we just gather up first char into our return value, and then we just loop through saying get the next character, and while we haven't hit the end of the file, that's the p is not none part, and while this p character is one of the allowed characters because it matches that regular expression we passed in, which in this case was just the same regular expression we used before, just saying it's either a dot or a digit. Then we just move on to the next character and keep on adding to the return value the answer we're building up until we stop finding any character that's allowed, and at that point we return it. So that was it for digits. Once we've returned back that value, we've got the number because we've obviously got to a character that isn't allowed in a number, for example, a space. So we've finished with that token, we yield it up. For symbols, it's a little bit more complicated. In order to recognize that we're starting a symbol, we look for either an underscore or a letter, but not a number. So once we've found that first character is a letter or an underscore, then we yield up something called symbol and we scan through. So this is calling the same scan function we just saw for numbers, but this time the regular expression we're passing in to say what's allowed in a symbol includes underscores, A to Z, and 0 to 9. So in lots of programming languages, symbols are allowed to contain numbers, but they're not allowed to start with numbers. And this kind of structure is an explanation for why, because when you're writing a Lexer, it's much easier to say anything that starts with a number is a number, and so therefore symbols can't start with a number. But once you know you're inside a symbol, then the other characters can be numbers because there's no ambiguity anymore. So this is the way we recognize symbols in Cell. Just starts with an underscore or a letter, and then scan through the rest of the characters in that symbol until we find something that's not an underscore, a letter, or a number. And the last bit of the lex function is just if we found any other character that doesn't match any of these patterns we were expecting, then we throw. So in Cell, because I'm opinionated about tabs, that includes tab characters. Cell will just fail if it finds a tab, or also if it found some other Unicode character it doesn't know about, because Cell only does ASCII, then it will throw. And that is how we lex a stream of characters. We've got a stream of characters coming in with no structure on them, and the iterator that comes back from this lex function is just going to be iterating through these tokens with a type and a value, which classifies basically bits, chops up bits of that stream of characters into something that we can understand, which will then pass on to the parser, which will put a structure onto it. So here's my kind of proof that it really works. Here's one of the tests from Lexer's test suite. So we lex this thing that just says print hello world. Pass that into the lex function. The lex function returns an iterator, so we use Python's list function to turn that into a list. And then we're just asserting that list is a list of a symbol with value print, and then a round bracket, and then a string with value hello world, and then a closed round bracket, and then a semicolon. And that's it for how we wrote our Lexer in Cell. It's a very simple Lexer, much simpler than you might find in a real programming language, but it contains a lot of the ideas. What it doesn't contain is having to go through more than one character in order to decide what type of token this is, but you can imagine how that might get extended. So I hope I've convinced you that this was a relatively easy bit of code to write. You thought that writing a programming language was going to be very difficult. Actually, at its kind of core idea, it's not that complicated. It contains sometimes confusing ideas because you're writing code that itself is talking about code. But the actual amount of code you have to write is not that much. Now, the Lexer is the easiest bit, but we'll go on to the parser next time, and although it's harder, it's not that much harder. It's a little bit longer. If you would like to encourage me to write videos, please donate. Set up a regular donation to me on Patreon. If you would like to play a fun Android or not Android game called Rabbit Escape, which is a bit like Lemmings, where you have to try and help your rabbits escape from the worlds that they're stuck in by giving them little tokens that help them climb up walls or build bridges or things like that, go to artificialworlds.net/Rabbit Escape, or look for Rabbit Escape on the Android Play Store. More videos on YouTube. Follow me on Twitter at j.p.beaubien. My blog is artificialworlds.net/blog, where you'll find things I've found out about programming. You'll find my videos on there. My open source projects are on artificialworlds.net. I'm currently working on a game written in Elm, which is a very exciting language that should hopefully replace JavaScript and make everything much less error prone. You can find my GitHub projects on GitHub. See you next time.